Hello everyone and welcome to another lesson. My name is Nick and today we're doing chemistry. I'm going to be looking at covalent bonding. Now, in the last lesson, we looked at electronegativity and how knowing the electronegativity difference in the atoms will help us decide what type of bond we have. So let's look at hydrogen gas, which is H2. Hydrogen gas, right? The bond of hydrogen is going to look like this. And so in these next three videos, we are looking at intramolecular bonding, meaning bonding within the molecules themselves. So within this H2 molecule. So what I'm going to do is I'm going to start by looking at the electronegativity differences, which is our change in E. And we see that the hydrogen has an electronegativity of 2.1. And there's two of them. So that would be equal to 0 when we looked. And so when we look at our table, 0 to 0.4 is a covalent bond. And meaning that it's also non-polar. And because we look at H in the group 1, row 1, column 1, they're both H+, so there's no overall charge here. There's no positive or negative end. So that's why we say that it's non-polar. I'll go into the polarity in the polar covalent bonding section next, but we can just see that basically because it's the same type of element, there's no difference in electronegativity, and so we're going to have a covalent bond. So even if you don't know the electronegativities off by heart, you know that something like oxygen, right, because they both have, so O2, also a gas, both have 3.5. And so the change in E is going to be 0. So those are all our diatomic molecules with the same element. Both atoms are the same element, so we're going to have a covalent bond. So a covalent bond happens between non-metals. You see that with hydrogen and oxygen and nitrogen gas. So we know then that this covalent bonding happens between, put this in big, two non-metals. Okay, so we can look at another type of polar covalent bond. Let's look at something that exists in nature. So that would be CH4, carbon. So CH4 looks like this. And we can say that this is covalent and non-polar because the symmetry of this means that there's no positive and negative pole in this element. So more on that in the ionic and polar covalent bonding, but we can also just look at the electronegativity differences. So we have hydrogen, which is 2.1. Well, let's start with we'll do hydrogen 2.1. Carbon, always put the element with the highest electronegativity first, because then we get 0.4, and we look at our table, it's covalent and it's non-polar. What I want to do now is also just look at BH3 as well quickly. Now, if we look at the electronegativity of hydrogen, it's 2.1, and boron is 2. We get our change in E is 0.1, and it's covalent. Now, there is something else to look at when we are looking at the covalent bonding and whether an element or a molecule is polar or non-polar, and that is when they look at the structure of the molecule itself. So I want to compare B and H quickly. So we're going to go in a little bit more depth into how these bondings work by looking at valence electrons. So boron has 1, 2, 3 valence electrons. 1, 2, 3. And hydrogen, each of them has 1, so they bring 1 to the party. 1, 2, and then there's 3 of them. So I'm going to put this one here, and I'm going to put that previous one here so that we can see that there are the 3 valence electrons that boron has contributed, and there are the 3 that hydrogen in yellow has contributed. So this is looking like what we call a Lewis dot structure. And what we see here is there's no spare electrons. So we've got this nice symmetrical non-polar molecule. So often when you get to higher points of chemistry, you have to draw these molecules in order to see the polarity. But you can just check the electronegativity as well, which is much easier. But I just thought I'd show you because some of you may be doing the type of trigonal planar and planar molecules. And so this here is a trigonal planar molecule, tri meaning 3, and it's on a single plane, and there's no bending going on. And we'll compare that to a polar molecule quickly, no, but I will go in the next lesson into this again. But it's probably handy just to see the difference between 2. So let's look at something similar to BH3, and that would be NH3. So let's look at N. Now N brings 1, 2, 3, 4, 5 electrons to the party. And hydrogen brings 1. Now hydrogen, unlike other molecules which often want usually want 8 electrons around the center, in this we have an exception because there aren't 8 electrons for the boron to have. It's not enough. But now in NH3 there are 8 electrons around the center, and then hydrogen has its 2, so it's happy as well. But now what we see is there's this lone pair. And so we have what's called an overall charge of negative on the central atom, and we've got on the outer H plus, we could have a plus charge. And so here we have a polarity involved. We've got a negative and a positive. As I say, more on that in the next lesson. But I just thought I would show you that a covalent bond we see is a lot more symmetrical, and it doesn't have that imbalance of electrons to create the polarity. So that's covalent bonding. As far as drawing the molecules, that's a little bit more confusing, but just look at the electronegativities in the periodic table, and if you see that it's 0 to 0.4, you can say that it's a covalent, pure covalent bond, meaning nonpolar. I should just add, you might see this as written as pure covalent. Pure covalent. rather than polar covalent, which we're going to be doing in the next lesson. So these are our non-polar covalent bonding molecules. There's plenty more, and you can just look at your electronegativities to figure out which ones they are. So if that lesson helped you, please find the like and subscribe button so that you get notifications on when the next lesson's coming up, and like with your friends and all that good stuff. And I will see you in the next lesson.